Okay. Let me put this over here. Oops. Good afternoon and welcome to Lecture 11 in MAE 113, Calculus for the Liberal Arts. We're going to be covering applications and rates of change. I'm Richard Kohar, and please make sure that you say hello or give a thumbs up in the chat to make sure that the audio is coming through okay. Excellent. Thank you, Maria. Nathan, we deserve more time for the tests. There's Javier. Excellent. Thank you. Thank you. Okay, so let's start. So today we're going to start off with an example. We're going to differentiate this function y equals x cubed minus 3x plus 5 over x to the fourth minus 1. So, again, using the quotient rule, okay. So, the quotient rule, again, if we have, say, f over g, and we're going to take the derivative of that, derivative of the top function times the bottom function minus the top function times the derivative of the bottom function, all over g squared. So, what we need to do is need this, and so in the top part, we're going to do f, so we'll do f prime, and then we'll have g, then we'll have a minus, then we'll have f and g prime. And then, of course, that's going to be all divided by g squared. So we're going to take the derivative of the top function right here. So this is our f, and here's our g. So taking the derivative of the top function, we have x, okay, so that becomes 3x squared minus 3. And we write the g function again, x to the fourth minus 1. We have f, which is x to the 3 minus 3x plus 5. And I have to take the derivative of the bottom, so that's 4x to the 3, and that's it. And then completing that, we just need to write the g function, so that's x to the fourth minus 1, all squared. So with that, so we can expand that out. Now I'm just seeing some of the comments in the chat about the quiz. If there's anything that you have an issue with in terms of the quiz, something, there was a technical glitch or something like that, send me an email through the RMC address, and we can sort that out. we'll have a minus. So in this case, we have 4x cubed times x cubed to the 6th. And then we have a minus 12x to the 4th plus 20x cubed. Somebody asked about reviewing the quiz. Of course, we can always do a one-on-one review of the quiz during office hours. Office hours are on Thursday from 1 to 3 p.m. Okay, well, as per the course outline, what you can do is send me an email and we can set up a time to have a session to review the quiz. So just send me some times where you're available and we can work out a time. So what I'm doing right here is I'm distributing this negative. So I have a negative and then a plus and a negative. Cubed. Okay, and we're almost finished. So all we have to do now is just kind of simplify that. That's, what do I see? I see, well, I start looking for the 6's here. So that's a minus 1, so just minus x to the 6th. Then the next one that I have is to the 4th. So I have 12 minus 3, so that's 9. Then the next one I have is minus 20x cubed minus 3x squared plus 3. Do you not expand the denominator? I don't think you have to in this case because we tried to keep it simplified. So I would leave that alone. But this case, there's a whole bunch of terms here. Like here, I was trying to see if I could find some common factors and I couldn't. So instead I expanded it out and just collected like terms. And that's the simplest I could get it. So hopefully that answers Joey's question. Okay. Let's see. Let's do another example. Oh yes, and that was a question. I think this was from section 1.6. And this was 18, question 18. So again, I was doing questions that weren't on the assignment, but they're, close in difficulty. So I was just doing some even questions. And this one is another one from 1.6, I think, as well. And this is question 50. And what it's asking for is to find the slope of the tangent to the graph of f of x 2x plus 1 over 3x plus 1 at x equals 1. Okay, so the slope of the tangent. So again, this should be a question that you should be able to answer in under a minute. So how would we do this? The first thing is, I'm going to just explain it before I write everything out. The idea is that you need to find what the derivative is. The derivative is, in the graphical sense, the tangent slope. And then what we're going to do is we're going to plug in that number, which is x equals 1. So the derivative at 1, and that will be the slope of the tangent at that point where x equals 1. So this is a quotient function, so we're going to be using the quotient rule. So again, start the clock. The top derivative is 2, and then we multiply by the bottom function unchanged minus the top function times the derivative of the bottom, and that's just 3, all divided by 3x plus 1 squared. That's just using our rule. Then substituting in our 1, we get 1. So the 1 goes in here, so that's 1 times 3 is 3 plus 1 gives me 4 minus, and then again substituting in the 1, 2 plus 1 is 3. 3 times 3 is 9. Divided by, and then again the x is 1. 3 plus 1 is 4 squared. So that equals 8 minus 9 all over 16, which gives me negative 1/16, is the slope of the tangent at x equals 1 for f of x. Okay? So again, for some people that are asking, this is kind of sloppy, but I'm doing it a little bit quick. And some people, like Maria, who was asking me, like, do you simplify something? Do you simplify? Well, again, it depends if you need to, if you need a final answer that's being left with in terms of x's. But sometimes you don't have to simplify. If you are just going to plug it in the number, you can quickly do your multiplication, get your final answer, and then you're done. So again, I keep saying it depends. The reason for that is because it depends on the question. Good. Somebody was timing me. Less than a minute. Good. They should be quick questions to be able to test, little rules or to be able to do, I don't know. It basically, the quizzes are designed to be skill testing. Table 1.2. Oh, okay, yes. I'm going to do one of these. I don't think they give kind of an example like this in the textbook, but, these are kind of interesting for test purposes. So, for example, let's say that I have a function, and these are the values for it. I have I have x, I have f of x, I have g of x, I have f prime at x, I have g of x, g prime of x. I'm going to draw a little. So we have 4, 2, 3, 5, and 4. And the question is, find the derivative of the function f of x over g of x at x equals 4. Okay, so doing the derivative, what this is testing in this case is what is the definition, or what's the quotient rule? So again, it's the derivative of the top function times the bottom function minus the top function times the derivative of the bottom function, all divided by the bottom function squared. Then what we're going to do is we're going to evaluate this at x equals 4. So that's what that line is. Evaluate at x equals 4. So the derivative of f of x at 4, so again, you could just think of it as, here's f at 4, g of x at 4, minus f at 4 times the derivative of g at 4, all over g at 4 squared. And using our values, we just plug them back in. So it's 5 times g, which is 3, minus And then we have 4. So this is 2. So I'm just plugging in the values. All divided by 3 squared. So hopefully we remember our multiplication, which is we have 5 times 3 is 15 minus 2 times 4 is 8 divided by 9. 3 squared is 9. Okay. 15 minus 8. And then divide that by 9. So we have 7/9. Right? Working backwards, 8 plus 7 is 15. Okay, and these are relatively prime. I don't have to do any reduction of the fraction. So again, for quizzes and stuff like that, you know, you can have a question maybe on the next quiz or on the next test where I could give you values like this, and then I give you a function like that. And you just have to apply the differentiation rule, plug your values in, and you can get a nice number at the end. Okay, was there any questions about this example before we move on? Okay. So let's do some applications in economics and business. So let's talk about cost functions. So I should maybe give it a little title. So we're doing applications in business and econ. Can you just slow down in the future a bit? Okay. Yes. So, okay, in this one, I'll take my time a little bit. We're going to talk about costs and cost functions. So if it costs a company, and we're going to say a function cx. So it's a function of cost to manufacture X units. So units could be kind of anything. So if it goes from widgets, pens, missiles, bullets, tanks, there's a cost for manufacturing a certain product. This is called, obviously, the cost function. And if there's an increase or a decrease, so let's say that if the number of units increases, and we're going to pick an x, so let's say x1 to x2, then the additional cost is that change, right? So it's that delta C, and we're going to do, and our delta C is the change in the two costs between the cost of x2 and the cost of x1. So we'll do a difference. Perfect. And then since we're talking about rates of change, well, we can also look at the average rate of change between doing x1 and x2. So then the average rate of change of the cost is, and so when we do that, it's the change in the cost over the change in the units. So again, we can just write out our change, which is the cost of x2 units minus the cost of doing x1 units, all divided by x2 minus x1. Or equivalently, the delta x could be the change from going from x1 to x2. So going from x1 to x2 is our delta x, which means then that the x2 is equal to x1 plus our delta x. So equivalently, we could write it as replacing our x2 with what we had up here. We have our x1 plus delta x minus the cost of x1, all divided by our delta x. And that should already make you have goosebumps, because that looks like something we've already seen. And if we have a limit involved in there, then we can actually go from having the average rate of change to the instantaneous rate of change. So again, we're getting to the idea of the derivative. So make sure that we label our numbers. So we got 2. And we have 3 here. So what I'm saying is that as we let the delta x go to 0, in what I'm going to say is in the let's call this a star, so I'll put a star here in the star equation there, we approach the instantaneous rate. Of change in the cost and this is with respect to the number of units produced. The number So when we do that, so what we have then is we're going to have a limit, and we're going to let, following our idea here, we're going to let that change in the units get really small. And that's kind of, that's the derivative. Now when we do something like this, we go from the average rate of change in the cost to the instantaneous rate. And in an economics or a business setting, they refer to this as the marginal the marginal cost. And so we could also write this using our Leibniz notation, which is the derivative of the cost function with respect to x. Okay, so there's a small note that I should I'll write in some sky blue. So just as a small remark, just a technical remark, which is that the values of the units themselves, x, take on integer values. So, and that's my z for integers. And remember, those integers are like -3, -2, -1, 0, 1. So, you know, counting numbers with 0 and the negative numbers. It might not make sense does it make sense to let the change of x go to 0? Maybe not. But it's one of those things that we use so that we can apply calculus. And the reason for that is maybe not. But what we're going to do, so that in order that we can use our tools of calculus, we just assume that the cost function itself is continuous. So that if it's continuous, then we can use our tools. Or in other words, we can use derivatives. Okay, so that's what we're going to do. We're going to make sure that when we're using cost functions, we approximate it, or we model it using a continuous function, even though we know that we can't say have like half a unit, because that's just not possible. We just make, discrete objects. So again, we end up approximating the cost function with a smooth continuous function. Is everyone okay with that so far? So it's just a little technical point to make, because you could potentially raise that you know, can we do a derivative on that? And the answer is, if we make that assumption, yes. Okay, so marginal cost is the derivative of the cost function. And so we'll just write it out. So we can't use delta x goes to 1. They usually make that the change in the unit go down to 0, so that becomes instantaneous. I think if it's with 1, then it's still kind of like an average. Yeah. Okay, so Maple said, why don't we let that delta go to 1? Okay, well, okay, let's, following along with what he says, so let's do that. So let's take that delta x equals 1. And we'll say that x is really large, is a large number. Then we have an approximation that we can use. So we can use this derivative here. So we use cx prime is approximately equal to, so this is that's the approximate sign. Different people use different things. As far as I know, with the American Mathematical Society, they prefer the double tildes. So that's what we're going to use for our approximately equal. So I'm trying to keep universal standard notation, but while everyone keeps saying that math is a universal language, it still has regional dialects across the globe. Oh, and of course I was talking and I wrote out the wrong thing. I just wrote out that derivative, and what I wanted to do was I wanted to actually write out the approximation. So by taking that really large, that means that this is going to be equal to 1, which means that the derivative is approximately equal to just taking the difference between x plus 1 minus x. Sorry, so it's the cost of x plus 1 objects minus the cost of x objects. And so what that's saying, using this approximation, what this is saying is that c prime of x is approximately the cost of producing one more unit. And so that's what they kind of mean by marginal. So if you have a cost function, you can tell me how much it costs to make X units. And then if you asked me what's the marginal cost, what that is telling me is that given that you've made 1,000 objects or 1,000 widgets or whatever, the marginal cost would be you're asking is what's the cost of producing the 1,001st widget or object. Okay. Okay. Cost functions in general. Let's see. Well, that was the root of my question, because in econ we typically consider the margin to be the cost of producing one more object. Exactly. So this is an approximation. Excellent. Cost functions in general. I'm going to write this. Here's a cost function. And I'm going to write it out as a polynomial, so I can have it as, I have a constant term a plus bx plus cx squared plus dx cubed plus so on and so forth. By the way, this is it's a polynomial. And of course you know that already. But why is a polynomial interesting is that in this case, this is a continuous polynomial. And because I have a continuous function, I can use a derivative. it's differentiable. That's something to remember. It is a theorem, which is that if a function is continuous, so as f is continuous, that implies that f is differentiable. Okay? So if it's continuous, it's differentiable. But notice that it's an arrow. It points in one direction, and I have done it for a very, there is a reason for it, because that arrow cannot go in the reverse direction. The reason for that is that not if f is differentiable, it does not mean that it is continuous. Or is it the other way around? We should investigate this other time, because maybe I made a mistake. Let's take a moment and think about this. So the question is this. I have a continuous function. I have y equals the absolute value of x. Just a quick way of doing it. Now, this is a continuous function. It's a straight line. This is a straight line. These are made up of it's a polynomial going this way, and I have another polynomial going this way. But remember, the problem I have with this is I can draw a tangent to this. This is fine. I can draw it on this side. I can draw a tangent on this side. The problem I get to is when I get to this point right here at x equals 0, well, where do I draw where do I draw the tangent? So at this point, x equals 0, I can't draw a tangent. So at this point, it doesn't exist. So in this case, y of f of x is continuous, but not differentiable everywhere. Could it not be a horizontal line? Sure, it could be a horizontal line, like I've drawn right here, like with the x-axis. But again, it has to just touch the function at one point. So what is it to stop me from drawing this? Or this? Or this? Or this? That's the problem. I don't have a unique tangent. It could be, I could draw any of those, and that satisfies that definition of the tangent. So because I can't draw a unique tangent to it, it's not differentiable. And I believe in some high schools they would have called this a corner. Corner, C-O-R-N-E-R. It's a corner. So I can't, draw a tangent. It just kind of flops everywhere. So I have a continuous function, but it's not differentiable everywhere. So what I've done is shown that it can't go this direction. I can't go from continuous to differentiable. We will come up with an example where We'll go through a couple examples maybe later where we have a differentiable function and show that it's continuous. So again, I should be careful because I made the incorrect direction here. But because this is a continuous polynomial, it is differentiable everywhere. So okay, so it's a continuous and everywhere differentiable function, so we can apply our derivatives to that. So it's differentiable everywhere. Okay. So we're looking at this cost function. Cost functions, so we have A, this is usually something like a fixed, this is a fixed cost. So fixed costs can be like rent, heat, initial startup costs. Like for instance, if we're going to do a press, like we're going to set up a press, or we're going to machine parts, there's an initial tooling for it, so that's kind of a fixed cost. We have other terms like X. So for instance here, that's B, so it's a linear relationship with the amount of units that we're going to produce. So this could be, for instance, so this is like a linear cost. And that is something like, you know, a direct relation to the number of parts that you're going to produce. So for instance, it could be like in raw materials. You know, we could get up into other, these are like quadratic costs. So here we have quadratic. This could be like something like labor or overtime costs, etc. But, you know, this is a fixed cost. There's kind of a linear cost, a quadratic, so on. So using that, let's use number 4. So let's do an example here. And we're going to use Acme. It's the American company that makes everything. And it's a large producer of propellant. Let's say, I guess they call it like smokeless powder. And the the management estimates the cost in dollars. So let's say, let's write out the function. So they have a cost function, and it's 25,000 plus 1.3 x plus 0.00001 x squared. So that's the cost. So cost of making X units of, and it's 8-pound bags of propellant, lbs, pounds. So again, we can look at kind of this Acme cost. So again, this $250,000 is our startup cost. So it whatever the tooling or the whatever it took to basically get to the point where we can start manufacturing smokeless powder. And then it costs probably about $1.73 to make each bag based on the materials. And then this 0.0001 x squared is probably something along the lines of like labor costs, so that as we make more bags, it's probably going to run into overtime, and so it quadratically increases the cost. Hopefully I didn't. So what we should do then is we're going to find the marginal cost. So find the marginal cost when we have x equals 1,000 bags. Okay, so when we look at the term marginal, it means that immediately we should be taking the cost function and taking the derivative of that. So we're going to take the derivative of that. So it's this function, $250,000. Well, we don't have to worry about that because that is a constant, and the rate of change of a constant is 0, so don't have to worry about that. The 0 plus, I have $1.73 times x. So again, the derivative of that is just 1.73. And then plus, I bring the 2 down in front. So that's 0.000001 times 2x. So just simplifying that. Okay. Then we need to figure out what the marginal cost is when x equals 1,000. So substituting in So by doing that, it shoves this 1, 2, 3. So the 1 should be, or the 2 should be here then. Right? Because we're going to move it 3 decimal places. 1, 2, 3. So it should be $1.73 2. So that's the marginal cost. And then the B, we're going to compare this to the actual cost of producing the 1,000. So again, this would be our estimate for producing the 1,001 first bag. Let's do the actual cost then. So the actual cost of producing the 1,000 first bag So it's finding the difference between 1,001 minus 1,000. So I have 250,000. Again, using my formula, or the cost formula there. I'm just writing this out. It is long. There we go. And when I work it out, that cancels. Okay, so when I do that, this cancels. I get 1.73, 1001 minus 1000. Plus 0.000001, 1001 squared minus 1000. So I'm left with 1.73. Plus I have 1001 squared minus 1000. And I would definitely be using a calculator because I'm at that point where I can't really. Who has a calculator available? Should punch it in 1001 squared minus 1000. Yeah, that question looks a lot like 53 in the homework assignment. Yes. Far too many zeros for doing it by hand. Yeah. That's kind of the nice thing about doing the textbook. Okay, so it's 2001. Okay, perfect. I think it's 2001 here. So that means it's 2, and I'm going to shove it approximately 1, 2. So this is going to be around 2 here as well. But I will check. Just to make sure that I'm not going to make an error. Okay, so that should be 0.002001. So 0.732001. So that's the cost of producing the 1001st bag. So it depends on what you consider to be close, but it's fairly close to what we have here. It's $1.73.2, and then this is $1.73.2001. So it depends, but you could say, so this is the end, so as a kind of a remark. Looks like is approximately equal to is a good approximation. Now notice for when x is large. Might not be the case when we make it a little bit smaller. Okay, let's move on to 5. So we have costs. Businesses are not only interested in costs, but in how much money they're making. So this brings us to the idea of a demand function. So we have a demand function. And we will be using the letter P of X. And that is the price per unit. Yes, that was from a long time ago. I remember people were, I think it was in the 80s that they had taken the rounding like to the thousandth or millionth of a cent, and they ended up collecting it, and over time they had a substantial amount of money that they had collected. So, it depends. If those little, millionths of a cent, they do add up depending if you have a lot of transactions or a lot of units that you're producing. So the price per unit, can charge if it sells X units. So that's the demand function. So you can see it as how many units the company can sell. Can sell when 1 unit is a particular price. Okay, then we get into the revenue function. Revenue. And we're going to use R of X is equal to the number of product or units that can be sold. So again, the revenue is how much money that the company's going to make off of a product. So it's going to be how many they can sell multiplied by the price. So this is the number of units sold. And this is the price, basically. So demand, revenue, and then we want to know, for instance, then, if we take the derivative of the revenue function, which is R of X prime, this is the marginal revenue function. So when we took the derivative of the cost, it became the marginal cost. We take the derivative of the revenue function, becomes the marginal revenue function. And what does this mean? It's the rate of change of revenue with respect to the number of units sold, to the number, that's a number sign, not a pound sign, not like Twitter or hashtags, I'm using that as number, the number of units sold. Okay, so we have that. Now that we've done all of our definitions, we've got a cost, we have a demand, we have a revenue. We could take the derivative of the revenue, and we can take the derivative of the cost. Okay, so let's say that we have a demand function. And it's given by 200 minus 0.01x. Let's get to the part that we care about, profit. Well, yeah, we're slowly working to that part, yeah. And of course, you know, not to jump the gun, but we have profit. And what's profit? It's the leftover money. The leftover money from when we have our revenue, and we have to take away our costs because we have to pay our bills, and that is the profit. So we have profit. So we'll call the profit P, capital P, of X. And then we're going to subtract the revenue minus the cost. And then of course, we could always take the derivative of the profit. So then if we wanted to do marginal profit, we can take the derivative of that, which means that I'm applying the derivative to this. And this is why I taught, you know, the sum rule in particular, is so that you can see that, okay, well, I have a sum, well, it's a difference of two functions, and I can apply that to each of these. And by the sum rule, it's just simply d of r by dx minus d of c over dx. Or some people may prefer to see it as r prime minus c prime. Okay, but that's where we're going to go. So this is the demand function. Yes, profit equals revenue minus cost. Yes. Okay, so I have a demand function, and we're going to continue this. So let's say that this is the demand function for Acme, for those 8-pound bag of powder. 8 pounds of bag. And you know, you could figure out, like, you know, a quick question would be, you know, what is the demand? Of 50 bags. Oh, what is the demand? And what I meant was of bags at $150. And so what we do then is we just insert that price. So we have P at 150. So it's 200 minus 0.01 times 150. where did I put the rest of the notes? I'm just wondering, did I do that correctly? It's 1.5. Okay, whew. I was like, yeah, I moved it too far. Excellent. Hopefully I did that right. 198.5. Make sure that everyone agrees with me before I go on. I'm not sure if I wonder if it locked up. Does everyone agree with what I did? 200 minus 1.5 gives me 198.5. Okay. So the revenue function, then all we're doing is we're just taking that demand function and multiplying it by x. So it's x times p of x. So it's x times 200 minus 0.01x. We'll do that squared. Perfect. And then we'll do C, which is find the marginal revenue function when x equals, let's say 3,000. So I have the revenue function here. So taking that, I have a derivative. I got to take the derivative of this whole thing here. So it's, I have 200x, so that's just 200 minus 0.01. The 2 comes down in front, so multiplying it by 2x, and then we reduce the degree down to 1. So I'm left with 200 minus 0.02x. Then, substituting in the value 3,000 into the derivative, because that's what we want, we're going to find the marginal revenue at x equals 3,000. It becomes 200 minus 0.02 times 3,000. 60, so 140. I think I did that right. So that is 140. And, you know, to interpret that, we should say that, therefore, that's what I got. Good, good. I was mumbling it as I was doing it, so hopefully. So therefore, the revenue from the 3,001st bag is $140. So when they produce the 3,001st bag of smokeless powder, they're going to make they're going to get $140. That's not their profit, it's their revenue off of that one bag. Excellent. Okay. So we already had a little bit of a preview of the profit function. So the revenue function is the total amount of money that the company earns, but again, the company has to pay for their costs. So if we subtract the cost from the revenue, we obtain the company's profit function. And that's what we're going to call, the profit function. So it's, let me just write that out. And we have our profit is our revenue. So it's our big bag of money that we've collected from the customer. And then we have to, pay our costs. So I'm going to use a capital P for profit, and then we have a revenue function minus our cost function. And then if you think derivative, in terms of our setting right now, derivative equals marginal. So that's what we're thinking, right? There we go. That's what we're thinking. That's not necessarily a person, could be a penguin. Yeah. And when we take the derivative of that, we get the marginal profit. And so again, it's the derivative of the profit function, which is equal to the derivative of those two functions, the revenue minus the cost, and by the sum/difference rule of derivatives. It's snowing here. Like it's a bit of a mess. So we get dr by dx minus dc by dx, or if you prefer, some people can write it as using our prime notation, r prime minus c prime. So now if we do a kind of, we have our example and it's continuing. What we're going to do is, using our demand function and our cost function from the previous example, we're going to find a profit and a marginal profit. So using the demand and revenue function, from the last examples, oh, I'm running out of paper. So what we're going to do is we're going to find the profit function and the marginal profit. So again, the profit function is our revenue minus cost. And then looking back, our revenue function was 200x minus 0.01x squared minus our original cost function, I'm just writing that out again. Okay. So again, be very careful about this part here. So I have my revenue function here. I have a minus, and then I have that cost function. People again forget to distribute that negative sign, and so they end up messing up their function. So again, we can clean that up. And distributing that. Okay. I have 200 minus 1.73, which is close to a quarter, which then makes that close to 27. So it's 27. And then we're taking off close. Okay, so that's 200 minus 1.73x. Again, just making sure, make sure I'm doing that right. So I've done this one and this one. The next thing that I have is I'm going to subtract the 0.01 from all of that. So that is just 0.0100001 x squared minus 250,000. Okay. Gross. But you know, not too bad yet. Let's take the derivative of that, which would give me my marginal profit. Taking the derivative of this is, you know, 198.27 times x is just 198.27 minus, I have all that in front there, multiplied by 2, so the 2 comes down in front, and I'm left with x. And then I have a minus $250,000, so that disappears because that's a constant. And so I'm just left with 198.27 minus. This 2 is going to go through and multiply these ones and change them into 2's. And there is my function. Okay. So, just to get ready for the next lesson next time, what I should try to introduce is the idea, now that we've done our applications, the next thing I should also introduce is the idea of higher order derivatives. Higher order derivatives. Okay. You can already hear someone shoveling outside. That's why I'm laughing. So nothing I can do about that. Higher order derivatives is when, okay, well, for instance, we have some sort of base function, say f, and if we wanted the rate of change of f, well, then that is f prime, or the derivative. Again, maybe sometimes you might be interested in the rate of the rate of the rate, sorry, the rate of the rate of change. For that, so you want to know not only, say, for instance, we have the profit function. If we took the derivative of that, that gives us the marginal function. So that would give us the rate of change of our profit. But maybe perhaps you want to know how quickly the rate of the profit for the bag on the next one is going to increase, so we can see if it's increasing or decreasing. So let's say that we could look at the rate of change of f. Now, what does that look like? Okay, well, if we used one little prime for this rate of change, and if we want to do the rate of change, then we're going to use two primes. Now, what does that look like if we were writing it with Leibniz notation? Well, for instance, if I was using f at x, and I wanted to do the derivative, then that becomes d of f with respect. So it's the derivative of f with respect to x. And if I took the derivative again, what that is really doing, or you can write it like this, which is d by like this. If we do the derivative again, it's d by dx times d by dx of f. So you can look at that as d squared over dx squared of f, or that's equivalent to writing d squared f over dx squared. So the second derivative, yes. Yeah. Just so that I could introduce, I have a derivative, and so some people start to call this the first derivative. So we have the first derivative, and then we get to the second derivative, and then we can get to the third. You can keep taking derivatives to your heart's content. Third derivative. Gets a little tedious after a while, so then ... you know, we can get to the nth derivative. And similarly on my right hand side here for the Leibniz notation, I can have d3 of f dx ... all the way down to d to the n of f to the dx to the n. So what does that mean? Well, it's like what I've done here. So if you wanted to do the second derivative, which is here, I'll cover that up. To get to the second derivative from f, well, we're stuck here, we're at f, we have to take the derivative, so we get to the first derivative. And then we take the derivative of this again to get us to the second derivative. Now, if you wanted to get to the third derivative, what you would do is differentiate this function again, and it will get you to the third derivative. So now that we have this idea of repeatedly taking a derivative or repeated differentiation, let's do a simple example. So, for instance, if I had y equals x to the 10th, then if I took the derivative of this again, so here's the first derivative. Well, from our power rule, the 10 comes down in front, so it's 10x to the 9th. If I did the second derivative, I don't do the derivative of this one, I do the derivative of this one. So the derivative of the second one, so it's d squared y by dy squared. So I don't touch that one. The 9 comes down in front, x, and the 9 drops down by 1. So we drop down a degree, so that becomes 8. So that becomes 90x to the 8. Here's the third derivative. Whoa, hang on to your hats. There we go. d3y by d . So same idea. We have 90. And then the 8 comes down in front. 8x to the 7th. 9 times 8 is 72. Plus the 0 placeholder, x to the 7th. And you can keep going to the 4th, the 5th. But eventually, we're going to get to the point where we're going to run out of exponents, and we're going to actually get to a point where we're going to have 0. So for instance, on the 4th one, so for the 4th derivative, the degree is going to be 6. For the 5th, it's going to be 5. For the 6th one, it's going to be to the 4th, 7, 5, 4, 3, 2, 1, 0, 8, 9, 10. So what this means here, that the derivative, where I take dy to the 10th of dy, or sorry, dx to the 10th, is going to be x to the 0 here, which means that we're just left with the constant. So we have a constant, and by the time we get to this constant, the next differentiation what happens then on this case? So if I'm taking the derivative of a constant, then on my 11th order derivative, what should this be? Yes, exactly. It should be 0. And then, of course, then the follow-up question would be, what's the derivative then when I take it again? I keep writing dy. So if I take the derivative again, what does that equal? Yep, it's still 0. Because the derivative of no change is still no change. So there's no change, no change, no change. Exact does not exist. Oh, wow. We need to look at this. Somebody wrote does not exist. So let's draw out that. So I have this, and here's my line. Whoops. So here is my function. Here's my y equals 0, which is 0 is still a constant, right? And so you should already be thinking, oh, it's a constant, so then it should be 0 as well. So picking two values here, if I wanted to take the derivative, I have 2 points here. Well, taking the derivative, my limit of, say, like, we'll call this x. Here's my delta x here. So I have my function. So this is going to be my x plus delta x minus x okay. Now at this point that value is still 0, and then I look at my f at x, which is here, and that's still 0. And without me even having to do any fancy arithmetic, or okay, any fancy algebra to simplify, 0 minus 0 is still 0. So I have a limit as delta x goes to 0, and I have 0 over delta x. So this whole thing, 0 over anything, is still 0. Now applying my limit rule of a constant, which is still 0. I don't have any delta x to go to 0, so I don't have to worry about that. So that is still 0. So what did I show? I showed that y equals 0, that the derivative is also equal to 0. Okay, is there any other questions? That was fun. We got to review and do some graphical explanation of from the definition of the derivative. That's good. But that's just higher order differentiation. It's just taking the first derivative, the second, the third, so on and so forth. Those are going to be important. I think we'll do something interesting then on Thursday. I'll show you some. We weren't able to cancel the delta x out of the denominator, so would that not result in dn? No. Remember, I have 0 over delta x. That's still 0. Remember, anything, or would that only matter if there was a number other than 0 in the denominator? Yes. Because the 0 ends up taking over. So for instance, like, I have 0 out of 3 on a quiz. That's equal to 0. I don't have anything. You know, it doesn't matter if you split that pizza up in 3 ways. If you told me that you got 0 out of the 3 slices, you got 0 pizza still. So it ends up dominating. And so the 0 over anything is still 0. Okay, Have a good afternoon, everyone. I'll see you all on Thursday. Thank you for tuning in, and I will post scanned copies of the notes from today's lecture up on Moodle. If you have any more questions about today's material or the homework or about the quiz, please send me an email and I'll answer those. Okay? Have a good night.